says our next guest needs no introduction. So David has received a number of prizes and awards for his work, including the Breakthrough Prize in Fundamental Physics, the Gruber Prize as part of the WMAP team, and the Shaw Prize. He's got a long list of professional and public recognition awards, and it's too many to mention here. I would take up the whole talk. And he's now co-chair of the WFIRST science team and on the board of directors of the Simons Observatory. In terms of the position, he's currently the founding director of the Center for Computational Astrophysics at the Flatiron Institute. And previously, he's currently also emeritus faculty at Princeton University, and previously he was department chair at Princeton. So David has visited us, South Africa, on a number of occasions, and hopefully we can welcome him back, once this pandemic is over. So over to you, David.
Yeah, so thank you for having me, and let me apologize again for my confusion over last week. And I look forward to being able to travel. I've always enjoyed my visits to South Africa, and looking forward in general to when we can travel again more easily. But that time will come. As Kavi mentioned, I'm now at the Flatiron Institute, which is a new institute. We're 4 years old. That's funded by the Simons Foundation, and it's a computational sciences institute. So we actually have 5 centers here: one for computational neuroscience, another computational biology, another in computational quantum materials, one in computational mathematics, and I'm director of the Computational Astrophysics Center, which has now grown to about 70 research scientists. And in the BC days, pre-COVID, before COVID, one of the things we benefited from was lots of visitors. And New York, for those who are visiting the US, is sort of the gateway to the US. So if you're traveling from Europe or from South Africa to Minnesota or Maryland, often you'll fly through JFK. When you do that, visit us. We're quite close. So hope to see many of you either here in New York or on my future visits to South Africa. So what I want to talk to you about today is sort of a tale of how we got to what we used to call WFIRST, but now we've renamed it after Nancy Grace Roman, the Nancy Grace Roman Space Telescope. Nancy Grace Roman was the first director of astronomy at NASA. She joined the agency back in 1958 when it was being set up. She was the highest ranking female administrator within NASA, and was someone who really structured how we do astronomy within NASA. It was under her leadership that NASA began building COBE, which would go on to discover fluctuations in the microwave background and earn its lead scientists Nobel Prizes. It was under her leadership that we built the first X-ray satellites that would earn the Nobel Prize for Riccardo Giacconi. And it was under her leadership that the Hubble telescope was built. So she's really someone who enabled much of most of space astrophysics for the late 20th century. And we were very pleased to be able to name the telescope after her. So the tale I want to tell today is sort of a series of related tales. I'll just quickly remind people of the motivation for some of the science by giving an overview of where we are in cosmology. I then want to talk about the US Decadal Survey and how the process that led to the creation of the mission. Then talk about the telescope itself, its design and science goals, the science choices that we're making right now for the mission, and conclude by talking about the road to launch. So for me, when I think about the motivations for studying dark energy, dark matter, one way to look at this is just to look at what we've learned from our observations of the microwave background, because I think that's somewhat the cleanest way to test our cosmological models. And also this gives me a chance to say a little bit about slip in some recent back results into this talk. And when we look at the microwave background, we're looking back, and most of what we see is an image of what the early universe looked like 300,000 years after the Big Bang, the time at which the universe made its transition from ionized to neutral. And when we go back to 2010 and look at what motivated the Decadal survey to talk about its top priorities, I think we have to look at what were the key observations we had back then. Of course, the observations of supernova, but for the microwave background, we had observations from space and ground, measuring the amplitude of temperature fluctuations as a function of scale that gave rise to this simple model. It's still our best cosmological model, a model described with 5 basic numbers: the age of the universe, the density of atoms, the density of matter, and the amplitude of fluctuations and how they vary with scale. And it's a model that's both simple and very strange. And it's while it's described by 5 basic numbers, it's a model that implies the existence of dark matter and dark energy. And those basic components of the universe are just not understood. And to jump ahead to the present, just to remind you, we have some recent results that have confirmed this basic picture from the Atacama Cosmology Telescope and the ACT telescope. We have team members from South Africa on the call. Is located in Chile, in the Atacama Desert, near the borders between Chile, Bolivia, and Argentina, in the mountains at about 5,300 meters. And it's a 6-meter telescope that's been surveying the microwave sky. It's now actually 14 years since we started that project. We've been working on this for a while. And if we look where we were, say 5 years ago, when the first, well, after Planck 2013, I guess 7 years ago, that had already confirmed the basic picture we had from WMAP, Planck measuring the microwave sky with much higher precision. You can see the Planck points shown in black and the ACT and SPT points in green and red. And just to give people a sense of the progress in this field, things continue to advance. Oh no, I didn't slip in. I'm sorry. I missed the slide. That was the slide I wanted to add. I didn't save the file. Okay, things continue to advance, and in 2020, we have even more data, like final release, improved data from SPT and ACT, and we still have the same cosmological model. We still have strong evidence for dark matter, strong evidence for dark energy, and don't know what they are. Now, we do have some interesting tensions while we talk about the model fitting. We have, as people have certainly heard, measurements from Hubble constant from Planck and large-scale structure gives values like 68. Measurements of Hubble constant from the CMB gives values more like 73. So this could be signs that lambda CDM is failing. It could also be signs that we're seeing evidence, it could be the new physics, or it could be systematics in the experiment. And one of the problems with giving Zoom talks is I can't really see people to know what they're thinking. So this is actually a point at which I'm going to stop the talk for 30 seconds, ask you to all turn your cameras on, and then to vote on whether you think this Hubble tension that we've been seeing is due to new physics that we haven't figured out yet, or systematics in one of the measurements. So let me stop and take a vote. It's always interesting to see. Okay, so I'm going to stop sharing. And then ask everyone to turn on their cameras.
David, I can't turn my camera because some reason, technical reason, but I vote new physics.
Okay, good. All right, so I'll give people another 10 seconds to turn on before we take the vote. Some people don't have their cameras on, that's okay, but for those with them on, who thinks it's new physics? Okay. Who thinks it's systematics? So I've been asking this question, and the one thing I can tell you that correlates with voting for systematics is age. Old people, like myself, tend to say, oh, it's going to be systematics again. But I hope the younger people are right, because they're the ones who are going to figure out what the new physics is. But since one of my many jobs is selling the mission to Congress, I always tell Congress it's new physics. It's more exciting than systematics. But let me now jump back in time to 2010 and talk about the process that led to the start of the W1st mission. So every decade, the US astronomy community gets together and puts out a report that identifies the top science questions and the highest priority missions. And we've been doing this since the 1960s. And we're right now in the midst of this process today. The way we run this process is we start out by setting up panels to discuss the top science questions. We usually have about 5 science panels. I led the cosmology panel in 2010. We identified as its top questions, what's the dark matter, what's dark energy, how the universe began. The 4th question we added was what's the properties of the neutrinos? And we identified correctly in 2010, gravity wave detection as the breakthrough area that was most likely to give us a surprise in the 2010s. Right now, we're in the midst of the 2020 decadal process, and we expect to have the new report out in about March of 21, identifying the big missions for the coming decade. So the way this process works is we begin with about reaching out to the community to solicit white papers. Back in 2010, we had about 500 white papers. In 2020, we've had close to 700 white papers on science. The panels read these white papers, discuss them, have a series of meetings, and then report out on the top science questions. This cycle, Dan Eisenstein led the cosmology panel. We then have prioritization panels, and I led one of the prioritization panels this year that looks at the missions and the projects, looks as input from independent costing, and then provides input to the a central planning committee or the main planning prioritization committee that then it puts together the full report. And right now that's the group that's meeting. Back in, and when we produce this report, we send it on to Congress, we send it to NASA, to NSF. NASA and NSF use this as a guide for what they want to do in the coming decade. NASA follows it pretty closely in terms of the missions it builds. The NASA leadership tends to see the community as the one that sets the scientific priorities, and their job is to execute these missions as effectively as possible. Sometimes we have friction from the White House that feels that they should be setting the priorities and directions, and this was particularly problematic in the Trump administration because a handful of astronomers with close political ties to Donald Trump played a big role in trying to set priorities. And that's actually the part of the process that led to the near cancellation of the mission multiple times. Three times the Trump administration, four times the Trump, no, they didn't set a 21 budget. Three times the Trump administration set the budget of the mission to zero and canceled it. This actually, unfortunately, led us to lose some of our international partners, like the Canadians, who should have known better and understood the US budget process better that the president proposes and Congress disposes. Fortunately, Congress, and for this, both sides of the aisles, the Republicans and the Democrats, felt that the National Academy and the US scientific community should be the ones setting the priorities, not a handful of people in the White House and their friends. So they actually fully restored the budget all three times. This was an effort that required really mobilizing the astronomy community. Our last trip to Washington, we had about 100 people come from 70 universities in 30 different states to come speak to their members about the need to restore the budget. One of the many things I did not know I would do in graduate school is be the person organizing people going down to Washington to lobby for money to restore scientific projects. But, you know, this just becomes part of the process. It was actually in many ways an interesting thing to get to do and actually get to see, as it were, how the sausage is made. And one of the things I came away from this experience is impressed with the people who are members of the professional staff in Congress and in the Office of Management and Budget. These are people who basically are trying to ask the question, given the budget we have, what's the best science we can do? And are very eager to hear from the scientific community. Should note this process of prioritization in a field for a decade has really spread from the US astronomy community that started doing this in the 60s to other areas of first NASA science or science from space, planetary science, and heliophysics, but also other areas like polar science and ocean science. And there's now processes in Japan and in Europe that in many ways parallel our decadal process for setting long-term priorities. And it's been an effective way of getting kind of broad community support and input for priorities over time. So in the 2010 Decadal Survey, the top priorities were build LSST, which is now the Rubin telescope, looking at studying dark energy, the variable universe, and really a broad range of applications in astrophysics. And DOE and NSF took up the challenge and have been working hard to build the Rubin telescope. And it should see first light, quite soon. And I think we can look forward to the Rubin telescope being one of the instruments really driving astrophysics in the 2020s. In space, the top priority was the WFIRST mission. And this was not even a mission that was proposed to the Decadal Survey. What was proposed to the Decadal Survey were three missions. One to study dark energy with an infrared telescope in space, surveying the sky. The other to study exoplanets through gravitational microlensing with an 1 meter infrared telescope in space. And one telescope to carry out an infrared survey to complement the optical survey for a wide range of problems in general astrophysics. And what the Decadal Survey did was say, wait, we have three proposals, all to build 1 meter class optical infrared telescopes with wide field of view. The technology is advancing. That's something that we know we can do. It's a lower risk project than the James Webb Space Telescope, which already was well over budget and behind schedule in 2010. And they recommended building W first. Now, the mission they recommended building was a 1.6 meter infrared telescope in space. And when they proposed that, at the same time, ESA had decided to go forward with Euclid. And that was decisions, what's happening. The European decision and the US decision were happening at the same time, with both groups not being cognizant of what decision they were making. I think one of the lessons we've learned from this is the importance of doing asynchronous prioritization, so that Europe does its prioritization knowing what the US had done, and then afterwards the US does its prioritization knowing what Europe has done. And we're now out of phase in our prioritization committees, and I think that will lead to avoiding this sort of problem. Now, what ended up happening worked out for the best. Unbeknownst to the people developing the Decadal survey in 2010, NASA was given an opportunity to get a 2.4 meter telescope from the National Reconnaissance Organization. Now, NASA is the US's third largest space agency. The Air Force and the National Reconnaissance Organization both have larger budgets, and the National Reconnaissance Organization has flown something like 15 telescopes that are Hubble-sized telescopes that, instead of looking up, point down. And they've been flying, say, the KH-11, which was the same telescope basically as the Hubble, had been flown before the Hubble and continued to fly for a while. The replacement for the KH-11 was a telescope with a much wider field of view that was developed around 2000. This project went over budget and had a bunch of technical problems and got canceled. But what was left behind were two complete optical telescope assemblies. And they initially, when the program was canceled, they were thinking of just destroying these unfinished telescopes. People involved with building the telescope felt they had the potential to be very powerful telescopes for astronomy. So the National Reconnaissance Organization approached NASA and asked them, do they want this telescope? This led eventually to what was one of the strangest phone calls I've gotten. I got a call from John Grunsfeld, who was then the head of space science at NASA. And John said, I was chairing the astronomy committee for the National Academy, and said, we just got a 2.4 meter telescope. Do you think we could use this bigger telescope to carry out the program for W first? And I said, I think so. It's a bigger telescope. You can usually do more. And then asked if I would put together a very quick study of what we would get, the scientific value of this. As soon as we started to think about this, we realized the telescope was big enough that we could also put not just a camera on it, but a coronagraph. And that led to the basic design that we had back in 2013, which we sort of stuck to since, of building a telescope with two main instruments: a wide field instrument capable of doing imaging and grism spectroscopy, and a coronagraph capable of imaging and taking spectra of exoplanets. And the idea with the coronagraph was, with a 2.4 meter, we'd have a telescope big enough to image super Earths and giants, have it as a stepping stone to imaging Earth-like planets, and have a place where we can really push and develop the technology. One of the challenges we found as we evaluated missions back in 2010 was that if you wanted to do interesting science and look at exo-Earths and you really needed to build a huge telescope and fly a coronagraph with it, but no one was willing to make that huge investment without having tested the technology. On the other hand, to test the technology, you needed to build $1 billion telescope, and no one wanted to build $1 billion telescope as a technology test. So this offers the opportunity to sort of piggyback on the wide field telescope and put a coronagraph on it, even if it's not the optimal pupil for a coronagraph, and use this to really push and develop our coronagraph technology. So this is what became the mission. NASA then asked Neil Gehrels and I to lead the Formulation Science Working Group, and we led a series of studies of the project. And that led to our developing a project that basically built on what was recommended in the Decadal survey, and is a mission that really rests on, I would say, the four scientific pillars of the mission. One is a program of general astrophysics. We've got a telescope with 100 times the field of view of the Hubble telescope and the same image quality. So you can think about every Hubble image you've ever seen and now make it 100 times bigger. So you can take, for example, the program, the FAT mission studying M31, and that took 400 pointings. WFIRST, you can do it in 2 pointings. Another key part of this is studying the dark universe, where I started in the talk, really making precision measurements of the expansion rate of the universe, large-scale structure of dark matter, and use that to infer, is general relativity failing on large scales? Do we see evidence for dynamical dark energy, and so on? Another important part of the mission will spend about 2 months a year looking at the galactic bulge, looking for microlensing events. The figure in the bottom sort of shows the complementarity between the Kepler mission and the WFIRST mission. In red, looking at semi-major axis in AU and the x-axis and planet mass on the y-axis. In red, you see the region probed by Kepler. Kepler, and now TESS, is giving us an inventory of planetary systems, showing us tremendous diversity, giving us real insight into how planets form. But it's a census that's very incomplete. It's only sensitive to inner planets. With microlensing, you're most sensitive to planets at about the Einstein ring radius of the host star. That translates to, depending on stellar mass, about 1 to 10 AU. So you can see that, well, Kepler is sensitive to kind of Earth-like or perhaps Venus-like planets. WFIRST would actually be a mission that, if it was observing our own solar system, would actually be able to detect 6 of the 8 planets, and actually would also detect 2 of the asteroids in the asteroid belt that are massive enough if you surveyed our own system. So this is, I think, a very exciting census that will really give insight into exoplanet formation processes. And also we'll be able to make, as I mentioned, huge steps towards exoplanet imaging by flying a coronagraph and really pushing the coronagraph technologies. One of my last international trip before COVID was to go to Stockholm, where I got to see my colleague Jim Peebles win the Nobel Prize. And when I look at the speeches given in Stockholm, the things that Jim talked about, those the big questions going forward: what's the dark energy? What's dark matter? How do the structures evolve to make the galaxy we see? How did the universe begin? What's its fate? These are the questions that we hope to address in cosmology. And here's Didier Queloz, who shared the Nobel Prize for the exoplanet work, talking in his talk about his top questions and what explains the diversity of planetary systems. And I think our microlensing work will provide very important complementary observations for those studies, really fill in this. You see pictures of the period radius relation with the whole right-hand side of the plot will be filled in by the observations of microlensing. The coronagraph will let us make progress towards understanding the properties of some of these exoplanets, particularly the more massive ones that we can image their atmosphere, look for things like methane through its photometry, and really make steps towards answering what I think of as really what perhaps the greatest question we want to answer in this field is there life out there? So returning to the telescope, and this is sort of the, thinking about W first, thinking about the Roman telescope, the image I want people to have of what its capabilities are is it's a telescope, and this shows its detectors with more than 100 times the field of view of Hubble or James Webb's NIRCam. So it really is going to be able to survey the sky in the infrared with incredible precision. That's sort of the capability we're thinking of. For dark energy, it will let us use all the different techniques for dark energy for supernova distances. It will push out towards redshifts of 2. It will be able to do BAO distances with spectroscopy using both H-alpha and oxygen-3. It'll be a very powerful telescope for weak lensing. And we can also use it to probe structure growth through looking at clusters, and it'll be a great complement to things that we're doing, for example, with the Simons Observatory, because we will go deep enough in the infrared to get weak lensing masses for even many of the more distant clusters. And there really are advantages to going to the infrared to do the lensing work. Galaxies are much more regular in the infrared, and that's also where we basically get to trace stellar mass. And it really will be going much deeper in its basic program than Euclid or DESI. This shows sort of the density of galaxies n times the power spectrum measured at the BAO peak, and you can see that we'll have much higher number densities that will let us get a much more sort of complete picture of large-scale structure. So it really will be sort of complementary to and deeper than Euclid, which will be flying a few years before. So for our weak lensing program, as we designed the telescope, we created what we call a design reference mission, which describes the plans on what we plan on doing. It's not necessarily, as I'll talk about later, what we end up doing in the end. The design reference mission, it says we should go try to minimize our systematics by going looking at about 2,400 square degrees, get to a galaxy density about 50 per arc minute squared. Our focus really is on systematic error control in designing this to make sure that we're not systematics dominated. So the plan is to measure shapes in 3 filters with multiple passes, multiple orientations of the telescope. We've designed the telescope to operate at L2, which will have a very small and stable PSF. Again, this will with the goal of really limiting the systematic errors. We took an approach of saying what we care most about is not minimizing statistical error, maximizing what's called the figure of merit, how well we measure dark energy parameters. But what we're probably going to care about in the end is having the best possible control of systematics in the design. And I think our experience in cosmology has been for precision measurements, we are limited by systematics, not by statistics. To give a sense of what we'll be doing in terms of surveys, the 10-year LSST depth is shown in the blue, where LSST will be surveying the sky in the U-band, G, R, I, and Z. The numbers shown are the PSF half-light radius in milliarc seconds, so about 0.4 arc seconds for LSST. In the red, you see the depth that we would achieve in our 2,400 square degree survey with the PSF of the Roman telescope. And in green, you see the Euclid survey depth. And you can see Euclid is actually very well matched to LSST one-year data. So I think when we're sitting in 2024, 2025, what's going to be a very powerful combination is LSST plus Euclid. When we look towards the end of the decade, looking at LSST plus the Roman telescope, that I think will give us this tremendously powerful data set and survey of the sky. Here's some of the parameters for depth of the survey. I want to emphasize that unlike actually with Euclid and with LSST, the survey designs are not yet fixed. The hardware is fixed. We're actually building it right now. But how we use it is really up in the air. And one of the things that a number of us have been thinking about, and this is a paper that appeared earlier this year on the archive led by Tim Eichler, is are there better ways of using the telescope for our cosmology program than the design reference mission? And remember, this design reference mission says cover about between 2,000 and 2,500 square degrees with a sort of range of numbers we looked at in our studies. That lets us survey the sky multiple times in multiple bands. Here we looked at an alternative plan where we said, let's say we want to do our photometric redshifts, not relying, instead of just using our own internal data, LSST is happening. We should be using data from the Rubin telescope and think about how we can maximize the combined science return from LSST and from the Roman Space Telescope. So the way we realized to do this is we can take the wideband that is actually put on the telescope for microlensing that covers almost the entire infrared from 1 to 2 microns that we're planning on imaging, take this wideband, and in 5 months, we can cover in the wideband the full LSST survey. For the entire LSST survey, you now have 0.1 arc-second resolution imaging across the whole survey, infrared photometry. This really reduces confusion in the LSST data, gives much more reliable photometric redshifts. When we looked at how well we could do in sort of estimating things like figure of merit, 5 months of W first added to 10 years of LSST improved the figure of merit by about a factor of 2.4 and outperformed our baseline design reference mission by more than a factor of 5. And I think this is such an attractive approach that I really hope that when we make decisions on observing strategies, which we'll do in the next 2 years, that we do opt for this wide survey to cover the entire footprint. And in fact, over the lifetime of the mission, I hope we end up surveying the entire sky in W band. It would take about a year of telescope time to have the entire sky surveyed in the infrared at the same resolution as the Hubble telescope. It'll be and depth corresponding to the 10-year LSST depth. It'll be I think a very useful data set for a wide range of applications in astrophysics. So when we think about these combined data sets, think about the synergies between Roman and Rubin. I have a chance now to put up a picture in their later years of Vera Rubin on the left in the orange, and Nancy Grace Roman in the blue. This is a picture taken about a decade ago at a conference at University of Maryland. They actually lived near each other in DC at the time. And what I was told by Ann Kinney, who was actually cut out of this picture, but with them at the time, that Vera was driving Nancy Grace Roman to the meeting each week. So you'd see them each day. So you'd see them come into the conference together all the time. But the two telescopes named in their honor will also end up working together. As I've mentioned already, improve photo-Zs. I think having Hubble quality imaging immediately available for everything you see in LSST will be terrific. It'll mean you'll have astrometry of—
Sorry, I couldn't quite hear you.
Astrometry of better than a milliarc second per exposure. We'll be able to identify brown dwarfs, AGBs, useful for studying AGNs. It's going to be a really rich data set that we can really get in just, in the end, about of order 14 weeks of data would actually cover the 10,000 square degrees with the lowest extinction. So that's sort of another version of this, is just look at the low extinction part of the LSST footprint. For astrometry, an interesting observing program to consider is to come back to this field every few years and get accurate astrometry and go deeper with time. I think for a lot of applications in galactic dynamics, this becomes a very nice complement to Gaia. This shows some of the trade-offs as we thought about this. This is the limiting AB magnitude you get to versus survey time. So with our 5-month survey, we can get to the depth of about 24.9 AB. That's at which point you're seeing about 95% complete for the LSST gold sample. And we achieve more than 99% completeness if we carry out this program of coming back to the same part of the sky 3 times over the lifetime of the mission. And this shows the improvement in cosmological parameters on the right. Another survey that we hope to carry out with the Roman telescope, and in fact, as we think about the planning, this is something we're hoping to do at the very start of the mission, is take the telescope and just take its, more than quarter square degree field and just image the sky in multiple bands. We've actually now added a K short band to this, and we would likely want to include this in the deep fields. And what we plan to do is identify the location of the deep field or deep fields. We may look at doing 2, one in the north, one in the south, sometime in the next year or so that we can encourage others looking at the sky at other wavelengths to go deep in some of the same fields. We're likely to pick some of the fields that Euclid is charting is identified as a deep field, and some of the fields that the Rubin telescope is looking at as part of its deep drilling program. And looking at these ultra deep fields, we expected to see large numbers of very high redshift galaxies that would later become targets for follow-up observations by the James Webb Space Telescope and by the next generation of large optical telescopes, the ELTs. So based on current models, we anticipate that this ultra deep survey would find, say, thousands of galaxies at redshifts greater than 10, and really maybe even tens of galaxies, the brightest galaxies, at redshift greater than 15. So this would give us a very interesting target list for follow-up work. And the ultra deep surveys would also give us data that we can use to calibrate our photo-Zs, to understand our systematics, and to plan for how we'll use this telescope. So I think the first thing we'll do is look here and look very deeply. I should note that the plan for this telescope is to make all the data we take available publicly immediately. There'll be no proprietary period. So this will be data that will be kind of accessible for people in the world. So this is something we hope to share with many others. So where are we with the project? It's been a long path to get here. The SNAP mission, which saw Perlmutter proposed in the 1990s, soon after the discovery of cosmic acceleration. So the first proposal along these lines. About the same time, Robert Lupton, Michael Strauss, and I were involved in setting up a workshop with Alex Refriger that Alex would then go on to lead Euclid for at the point. Thinking about building an infrared telescope to do a large field survey to complement the project that would then grow to be LSST. We've actually looked like we'll end up realizing that. In the late 2000s, DOE and NASA studied the joint dark energy missions. I was part of one of 3 studies to build this missions in the late 2000s. Those didn't go anywhere. Well, in sense, I guess they did. They went to help motivate the WFIRST recommendation in 2010. As I noted, we first studied these smaller versions of it. Europe developed Euclid. We then had the availability of this NRO telescope. When that telescope became available, at one point, NASA leadership was reluctant to encourage the use of it. They feared that if the astronomy community learned too much about this telescope, we'd get too excited and we would pressure Congress to fund it at the expense of other things they wanted to do. I actually organized a conference in Princeton summer 2013 to get this going that was done independent of NASA. I just invited people, and it produced a white paper that led to getting the SDT funded. With late Neil Gerrels, and we miss Neil very much, we started the pre-phase A study of this mission. And as we started to see what it could do, we were able to get strong support for it. And we're now been fully funded. This year is actually our peak budget spending year, so it should be easy to continue, or easier to continue getting full support in the coming years. Construction is well underway. We are working towards a launch in fall 2025. I anticipate we'll probably have a few month delay, but probably not so long, due to COVID. It's of course produced delays in supply chain. So if you asked me to bet on launch date, I would now bet on 2026, but things are moving forward. And you know, we're making good progress to building and flying this mission. So let me leave you again with sort of an image that I think you should have in mind when you think about what this telescope will do. Is take every image you've ever seen with Hubble, now make it 100 times bigger. I am very hopeful that we will be able to launch this mission within the next 6 years. And when we do that, the challenge will be for all of us in the astronomy community to think about, with a field of view of 100 times bigger, what are the things that we want to do in astronomy? So let me leave you with that question and thought about what we want to do with these things. This mission, it's a mission that will be a very powerful survey mission. One of the things that I think we should be looking at in 2030 as a product of this is a multi-instrument database that will show the sky measured in the optical from the Rubin telescope, the optical into the infrared by Euclid, the ultraviolet into the optical. The Chinese are launching in the decade a 2-meter optical telescope with a wide field of view off their space station that will also survey much of the sky, providing that a tremendous database. And the Roman telescope will be surveying the sky in the infrared. And Roman, actually, what I talk about is an infrared telescope. It can image and will have a red filter it's kind of yellowish. I've been trying to promote that we call it an orange filter, but it has not caught on. So this orange filter goes up to about 500 nanometers. So we'll go from there to about 2.4 microns. So we will have surveyed the sky from the near UV to the near IR at Hubble resolution. And this will be a tremendous legacy. And I think this wealth of data will drive a lot of progress across a wide range of problems in astrophysics. So let me kind of leave you with the thought of that tremendous data we'll have a decade from now, and think about all the things we can do with that data, how we'll combine it with microwave background observations, 21 centimeter, X-ray observations. I think we are fortunate to be living at a very exciting time in astronomy. Thank you.
Thank you, David. Thanks for that excellent talk. So we have some time for questions. Romeo?
Yeah, sorry. Hi, David.
Hey, Romeo.
So I was wondering what you thought of in terms of the spectroscopic complement to these types of surveys. Let's look at, let's say, in 2030. What do you envision as being the way we can get spectroscopy for a large sample of these imaged galaxies?
Well, early in the decade, we'll have data from the prime focus spectrograph on Subaru. And that's, so that's 2,400 fiber spectrograph that goes from the optical to the near IR. And one of the things we did was the Japanese are partners in the telescope, and one of their contributions is 100 nights of Subaru time to do follow-up work. So we're hoping, for example, on this ultra deep field that we'll have a lot of Subaru spectroscopy of that. But my hope is with Subaru and also with DESI, though DESI can be great, but it don't quite go deep enough for some of this, that when their core projects are done in the mid-2020s, that we will use those spectrographs to continue to do follow-up on these targets. And I think there's a very good science case for building a next generation spectrograph that will be a wide field spectrograph and do follow-up work. So I actually don't know what's in the Decadal survey for 2020. I am hoping that one component will will enable spectroscopic follow-up to these imaging surveys, because I think it's easy to look at all this and say we're going to have tremendous imaging data. We're going to want to actually get spectra of lots and lots of these things.
Hi, David. Yes. Thank you for the very nice talk. I'm Yinji Ma. So yeah, my question is, certainly those, I mean, these are really ambitious program, wonderful program. But I wonder towards what level of numerical improvement that can we answer the question that people posted in the, those fundamental questions that people posted in the Nobel Prize, seminar. Yeah.
So right now, the measurements we have of, say, the properties of dark energy, how close is the W, the equation of state, to 1, we're measuring at about the couple percent level. A decade from now, when we have all this data, our measurements should improve over our current values by more than a factor 10. So that's about the level of improvement we're looking at. Now, with that factor of 10, will we just know W is equal to -1 with more precision? That would be the least exciting outcome, but a possible one. The only guide I think we have to, for me, that sort of observational measurement of W being less deviating from -1 actually comes from observations of the microwave background of the primordial power spectrum. During the early universe, the universe went through a period of inflation. And if W is equal to -1, the spectral index would be 1. it's very clear from Planck, and it's clear from WMAP and now ACT, that NS, the spectral index, differs from 1. It's about 0.96, 0.97. That implies that during inflation, W was about minus 0.996, 0.995, somewhere in that range. A value that would be completely consistent with the current observations, but one that we would detect at more than 5 sigma 10 years from now with these experiments. So that's my hope.
But that's a good motivation. Yeah.
Right. Well, I don't see anyone else's hand up, so I think it just remains for me to say thanks so much, and yeah, for a really exciting talk.
Yeah, thank you for having me, and my apologies for last week, and hope to see all of you in person soon.
Okay. Thanks, David. Thanks, everyone.
Thank you.